Okay, now we shall study particle in a three-dimensional infinite potential well. In particular, we shall find wave functions and energy of a particle trapped in this three-dimensional infinite potential well. Let us draw the box, three-dimensional box here. Let us suppose this is the x direction, this is y direction, and this is z direction. And the length of the sides here along x and y and z directions are a, b, and c. Let's say the particle is somewhere inside the box, and we assume that the potential inside the box is 0 and outside the box is infinity. And the mass of the particle is considered to be small m. Inside the box the potential is 0 and outside the box the potential is infinity, so we can write down the potential function is a function of x, y, and z, which is 0 when x is in between 0 and a, and y is in between 0 and b, and z in between 0 and c, and infinity otherwise. Okay, so we write down the Schrödinger equation of the particle inside the box. We can write down this square by twice m del square psi, and we don't have potential energy inside the box, so the term is 0. And here we have total energy E of the particle and the wave function. This and write down here because E is 0 inside the box. Okay, let us say that this is equation 1 and this is equation 2. Or in Cartesian geometry, x is so the Schrödinger equation can be written as this. Let's suppose that this is equation 3. Now to apply the separation of variable technique to solve this equation 3, it is initially assumed that the wave function psi is a product of three functions each depending on just one coordinate system. So it take this wave function, which is a function of x, y, and z, and it is the product of three functions. One is a function of psi x, a function of x, psi y, a function of y, and psi z is a function of z. Okay, now then equation 3 then becomes we have this. Well, let us say this equation is 5. Now we divide this equation 5 by psi x, psi y, psi z. We obtain and we bring the last term on the right hand side. Let us say this is equation 6. Now one interesting thing we observe from equation 6, each term on the left hand side of equation 6, if we carefully examine, and we see that is a function of only one variable, and the sum of these three terms is equal to a constant right hand side of equation 6. And for example, if x is varied and y and z are held constant, then second and third terms will be 0 on the left hand side. Since the sum of these terms is a constant quantity, such a situation can exist only if the first term is independent of x. That means this term is independent of x. Similarly, the second term is independent of y, and the third term is independent of z. Let us suppose that then this term we call it minus 2m ex by h cut square, and this term we call it minus 2m y by h cut square, and this term is minus 2m ez by h cut square. If we take this, then equation 6 becomes is minus 2m ex minus 2m ey by h cut square minus 2m ez by h cut square, which is equal to minus 2m e by square, which gives us ex plus ey plus ez equal to ez. Let us suppose this equation is equation 7. And we have the first term is, you see, first term is this, second term is this, third term is this. So we can write down one by psi x d square psi x by dx square equal to 0. Say it. Or you can say this is equal to -1. So this is minus, and this is minus 2m ey by x square, and this is equation 10. Well, let us clean the board first and then we'll continue. It is now apparent that uh, those three equations, one for psi x, one for psi y, and one for psi z, that these each of these three equations actually equation for a one-dimensional infinite potential well solution equation, and so the solution of these three ordinary differential equations we can write down. For the first one, by applying boundary conditions, sorry, this will be Z. Okay, these three solutions um, um, will be multiplied to get the total solution. The total solution we multiply those, then we have okay, this is the solution. We have put the indices nx, ny, nz, and these nx, ny, nz are known as quantum numbers. Positive integers excluding 0. Excluding 0. And we also have x square h square pi square by twice ma square. And therefore the total energy can be written as the sum actually of the individual energies. So if you add these, we'll get okay. So this uh, gives us the energy expression. So we have found out the energy E, Nx, Ny, Nz, and we have also found the solution, the wave function of the particle trapped in the infinite potential, three-dimensional box, and we can say that it is obvious from the expression of the energy that the lowest energy, or we call it 0-point energy, occurs when nx equal to ny equal to nz equal to 1. The lowest energy or 0-point energy um, for this. Now we define a term that is known as degeneracy. What is degeneracy? In case of a particle in a three-dimensional box, if sides are equal, if A equal to B equal to C equal to say L, then the total energy E nx ny nz will become this. It is apparent from this equation that in a cubic box, the sides of the box are same, A equal to B equal to C equal to capital L. The energy depends on the sum of the squares of the quantum numbers nx, ny, nz if the sides of the cube are equal. Since the wave function corresponding to each state is characterized by three quantum numbers, it is possible to construct several excited states of the same energy. So we should actually mention it again. For same energy, if the wave functions are different, then we say that we have a degeneracy states. The energy is degenerate, the states are degenerate states, different states, but they have the same energy. The lowest energy level will be that for which nx equal to ny equal to nz equal to 1, and for this level the energy is given by, so if we take nx equal to ny equal to nz equal to 1, then we have the energy will be 3 h square pi square by 2m L square. Now for the next higher energy level, the values for the three quantum numbers are either nx equal to 2, ny equal to 1, nz equal to 1. Or we could take nx equal to 1, ny equal to 2, nz equal to 1. Or nx equal to 1, ny equal to 1, nz equal to 2. So let's suppose that this is case 1 and this is case 2. In this situation, the energy will be this, and it will be and so is 2 square plus 1 square plus 1 square, so 4 5 6, so this will be 6 each cut square pi square twice m l square. Now as I said, you could also have E1 to 1 but with the same energy, 6 h square pi square twice m l square. Also you can also show that E1 1 2 is 6 h square pi square by twice m. So you see in these three situations, when nx equal to 1, ny equal to nx equal to 2, ny equal to 1, nz equal to 1, the energy which is equal to when this, that means the state here is 2 1 1, here is 1 2 1, here is 1 1 2, but they have the same energy, so they have same energy. but the states are different. But states means wave functions are different. So in this case we have three possible ways for the nx, ny, nz set to exist, and these are the 2 1 1 1 2 1 and 1 1 2. These are three possibilities will give the same energy, though they represent different states. When energy levels of different states are the same, such energy levels are said to be degenerate. The number of different states belonging to the same energy is known as the degree of degeneracy. Thus, the energy level 6 squared square pi square by 2m L square. This one is threefold degenerate. Because we are getting three states or three wave functions, and these are we can say that the psi 211, psi 121 and psi 112. So three wave functions or three states, they have the same energy. We call uh, these three states are degenerate states, and we call it here threefold degenerate states or threefold degeneracy. The energy levels corresponding to different states are shown in table 3.1, that is shown in your PDF file that is available in your Google Classroom. For a particle in a three-dimensional box, this degree of degeneracy can be removed by a slight distortion of the system or by using a box of different dimensions. Okay, now we shall consider quantum well, quantum dot, and quantum wire. The problem that we have solved here is a quantum well. Where each side of the box is set equal to a constant. So, and if the length of the sides are finite, then we can say that um, the box is a quantum well. So now we discuss quantum well. Quantum dot and quantum wire. First, quantum well. Here, if our sides are equal, say, then we have energy and the wave functions. where the length L is finite. The above situation is known as a key quantum well. Okay, now we discuss quantum dot. Now this is like quantum well, only the difference is when L tends to 0. That means no dimension, or approximately equal to 0. So we say if A equal to B equal to C equal to L tends to 0, then we can write down the energy as Enx, Ny, Nz, and we say limit L tends to 0, and this is square pi square twice L square, and the sum of the squares of the uh, quantum numbers. You can write down the wave functions. Also write down limit L tends to 0, and then we have this. Okay, and next this one we say, okay, the above situation is known as a quantum dot. Finally, we consider quantum wire. Here, if A equal to B equal to L is not equal to C, and L tends to 0. That means two sides are equal and these sides tend to 0, but the other side which is open on both sides. So this is not actually a box. You consider um, z direction is open. The particle cannot be confined along the z direction, either positive z direction or negative z direction, but the particle is confined along x direction and y direction. So the length of the sides of the box, this is, you can say, box, but two ends are open along the z direction, and the two sides x and y, along x and y directions, they tend to 0. The energy and wave function can be derived. We have not done here, but easily these can be derived as this: Nx, Ny, and this is equal to limit L tends to 0. Now we have a square pi square by twice L square, Nx square plus Ny square. Because in these two directions, x and y directions, the particle is confined, so the energy will be like this, and along the z direction, particle is free to move, so the free particle energy will be h cut square kz square divided by twice m, where kz is the wave number along the z direction. This kz the wave number along the z direction. Okay, and the expression for the wave function, this one can be written as there will be a constant here and sin x by L sin ny by y by L, and along z direction is a free particle which is e to the power I k z z. This situation is known as a quantum wave. There are wide applications of quantum wave, quantum dot, and quantum wire in electronics and electrical engineering, and in particular electronic devices. We are not going into the details of this application here, but I hope that you have liked this analysis, and we are going to stop here.